Hello, in this lecture we will find out the value of line segment MN. In the drawing we have square ABCD, and we know that one side of square ABCD is equal to 12 units, that is to say AB equals to BC equals to CD equals to AD equals to 12 units. And inside this square ABCD we have a circle and a semicircle. The center of this circle is at point M, and the center of this semicircle is at point N. And we actually want to find out the distance between their centers. That is to say, the distance between point M, that is the center of this circle, and the distance between point N, that is the center of the semicircle. Okay? So, first of all, we will define the point of tendency of tangent AB with this circle as point P, and we will also define the point of tendency of tangent BC with this circle as point Q. We will define the point of tendency of diagonal AC with this circle as point R. We will define the point of tendency of diagonal AC with the semicircle as point S, and we will define the point that the semicircle touches the side DC of square ABCD as point T. In the next step, we will define line segment PB as A, that is to say, the length of line segment PB equals to A units according to our definition. And because of the fact that AB equals to 12 units and PB equals to A according to our definition, AB minus PE equals to AP. That is to say, AP will be equal to AB, that is 12 units, minus PB, that is 8. That is to say, AP equals to 12 minus A. Okay? In the next step, I will present to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. I will read rule number 1 again. According to rule number 1, the lengths of two tangents the lengths of two tangents from a common external point to a circle are equal. So actually we have a circle and this point, we define this point as point P. Point P is defined as an external point in relation to this circle. Why? Because point P is not located inside this circle nor on this circle, but it is located outside of this circle. Therefore point P is defined as an external point of this circle. So if from point P, the external point P, we will draw two tangents to this circle, the first tangent will be this tangent. We define the point of tangency of the first tangent with this circle is point A. Point A is the point of tendency or the touching point of the first tangent with this circle. Then we will draw the second tangent to this circle from point P, of course. So this is the second tangent. We will define the point of tendency of the second tangent with this circle as point B, or the touching point of the first tangent or the second tangent with this circle is defined as point B. And according to rule number 1, the lengths of two tangents, that is to say, the length of the first tangent is PA, while the length of the second tangent is PB. Then according to rule number 1, the lengths of two tangents from a common external point, that is to say point P, to a circle, to points A and B, are equal. That is to say PA equals to PB. So whenever you draw two tangents to a circle from a common external point, like in this case from the common external point P to this circle, then the length of those two tangents will be equal to each other. That is to say PA equals to PB. Okay? So actually we can implement rule number 1 in our drawing. Here we have the external point, point B. That is the vertex of the square ABCD, and from point B we have two tangents to this circle. The first tangent is BP. BP is tangent to this circle as point P. At point P, and we have the second tangent, that is BQ. I repeat again, we have tangent BP, and the second tangent is BQ, and according to rule number 1, the length of those two tangents will be equal to each other. That is to say, BP equals to BQ according to rule number 1. But according to our definition, PB or BP equals to A. So from this equation, A equals to BP equals to A, we will derive that BQ is also equals to A. Okay, here we can write down that BQ equals to A units. And because of the fact that BQ equals to A units, Then what will be the length of QC? QC, it is very easy to see that QC equals to BC minus BQ. Again, BC minus BQ equals to QC. That is to say, QC equals to BC, that is 12 units, minus BQ, that is A. That is to say, QC equals to 12 minus A. Okay? And if we focus at point A, the external point A, from the external point A, we have two tangents to this circle. The first tangent is AP, and the second tangent from point A to this circle is AR. And according to rule number 1, whenever you have two tangents from an external point to a circle, like in this case, from point A we have two tangents, tangent AP and tangent AR, then the lengths of those two tangents will be equal to each other. That is to say, AP equals to AR, according to rule number 1. Okay? But we have already found out that AP equals to 12 minus A, so we can write down that AP equals to 12 minus A. So from this equation, 12 minus A equals to AP equals to AR, we will conclude, we will derive that AR is also equals to 12 minus A. AR equals to 12 minus A. So we can write here that AR equals to 12 minus A. And if we focus at point C, from the external point C, from the external point C, we have two tangents to this circle. The first tangent is tangent CQ, and the second tangent is tangent CR. And according to rule number 1, the lengths of those two tangents are equal to each other. That is to say, CQ is equal to CR according to rule number 1. But CQ equals to 12 minus A, so we can write here that CQ equals to 12 minus A. And from this equation, 12 minus A equals to CQ equals to CR, we'll conclude that CR is also equals to 12 minus A. CR equals to 12 minus A, so we can write here that CR equals to 12 minus A. Okay? Again, if we focus on at point A, from the external point A, we have two tangents to the semicircle. Again, from point A, we have two, from the external point A, we have two tangents to the semicircle. The first tangent is tangent AD. Tangent AD is tangent to the semicircle at point D. This is the point of tangency. And the second tangent from point A, that we have is tangent AS. AS is tangent to the semicircle at point S. Point S is the point of tangency. So actually, according to rule number 1, AD is equal to AS. Because from the external point A, we have two tangents to the semicircle, therefore the length of those two tangents will be equal to each other, that is to say AD equals to AS. But according to what is given us in the question, we know that AD equals to 12 units. AD equals to 12 units. So from this equation, 12 equals to AD equals to AS, we derive that AS is also equals to 12 units. So we can write here that AS is equal to 12 units. AS is equal to 12 units. So we know that AS equals to 12 units. So what is the value of RS? It is very easy to see from the drawing that RS is equal to AS minus AR. Again, AS minus AR equals to RS. RS equals to AS minus AR. RS equals to AS minus AR, so that is to say RS equals to AS equals to 12 units minus AR. We've already found out that AR equals to 12 minus A, so it is 12 minus 12 minus A. We will open the brackets here and we will find out that RS is equal to 12 minus and minus is plus A. 12 minus 12 is 0. So we found out that RS equals to A. So we can write here that RS equals to A units. And in the next step, I will present to you the second rule, rule number 2. According to rule number 2, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. I will read rule number 2 again. According to rule number 2, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 2? The meaning of rule number 2 is that we have this circle the center of this circle is at this point, we will define the center of the circle as point O. And we also have tangent to this circle here. AB is tangent to this circle at this point. We'll define the point of tendency of tangent AB with this circle as point M. So write it down. M is the point of tendency of tangent AB with this circle. We will join points O and M together by a straight line. OM is the radius of this circle. I will define it as R. Why OM is the radius of this circle? Because of the fact that line segment OM starts from the center of the circle, that is to say it starts from point O and ends at point M, that is the point on this circle itself. Therefore OM is defined as the radius, because this is exactly the definition of a radius. Okay, so OM is the radius of this circle, and here the radius OM is drawn to the point of tendency. That is to say, the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. Therefore, according to rule number 1, whenever you have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to this radius. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay? A tangent to a circle, that is to say AB, is perpendicular to the radius, OM, that is drawn to the point of tendency. Because of the fact that the radius OM is drawn to the point of tendency to point M, that is the point of tendency of tangent AB with this circle, therefore the tangent AB will be perpendicular to this radius OM. That is to say, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay? We actually can implement rule number 2 in our drawing. Here we will join points P and M together by a straight line. Line segment PM is the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point M, and ends at point B, that is the point on this circle itself. Therefore, PM is the radius of this circle. And here the radius PM is drawn to the point of tendency, that is to say it is drawn to point P, that is the point of tendency of tangent AB with this circle. Therefore, whenever you have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to the radius PM. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 2. And we also know that all the angles inside the square are right angles, that is to say they are equal to 90 degrees. Therefore, angle ABC, that is 1 out of 4 angles inside square ABCD, will be equal to 90 degrees. We will join points M and Q together by a straight line. Again, MQ is the radius of this circle. Why? Because it starts from the center of the circle, that is to say from point M, and ends at point Q, that is the point on this circle itself. Therefore, MQ is the radius of this circle, and the radius MQ is drawn to the point of tendency, that is to say it is drawn to point Q, that is the point of tendency of tangent BC with this circle. Therefore, whenever you have a radius that is drawn to the point of tendency, then the tangent BC will be perpendicular to this radius MQ. BC perpendicular to MQ. That is to say, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, so we'll focus on quadrilateral PBMQ. In quadrilateral PBMQ, this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Plus the size of the fourth angle, that is actually angle PMQ, this angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, here we will subtract 270 degrees from this equation, and we get that angle PMQ, the angle that we are looking for, angle PMQ is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. So we can write here that angle PMQ, this angle is a right angle, it equals to 90 degrees. Therefore, actually, in quadrilateral PBMQ, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So, quadrilateral PBMQ is a rectangle, at least a rectangle, but I write it down that is a rectangle. Quadrilateral PBMQ is a rectangle, and we actually have rule number 3 that states that the opposite sides of a rectangle are equal to each other. I write it down. The opposite sides of a rectangle are equal to each other. I write again, rule number 3, according to rule number 3, the opposite sides of a rectangle are equal to each other. That is to say, in rectangle PBMQ, according to rule number 3, PB equals to MQ. According to rule number 3, PB equals to MQ, but according to our definition, PB equals to A. So from this equation, A equals to PB equals to MQ, we will derive that MQ is also equals to A. MQ is also equals to A. Here we can write down that MQ equals to A. Likewise, according to rule number 3, BQ is equals to PM. BQ is equals to PM according to rule number 3. But we've already found out that BQ equals to A. You can write down here that BQ equals to A, and from this equation A equals to BQ equals to PM, we will conclude that PM is also equals to A. PM is also equals to A. So actually A, that is actually also the radius of this circle, actually all the sides of quadrilateral PBMQ are equal to each other. Therefore, quadrilateral PBMQ is a square. Okay? And we will find out the value of line segment SC. What is the value of SC? SC, it is very easy. It is very easy to see from the drawing that the value of line segment SC, it is equals to RS, it is equals to RC minus RS. RC minus RS, RC minus RS equals to SC. Okay? So SC equals to RC, and we have already found out that RC equals to 12 minus A. It is written here. Minus RS. We have already found out that RS equals to A. So SC is equals to 12 minus A. That is to say SC equals to 12 minus 2A. 12 minus 2A. We write here that SC equals to 12 minus A. What is the value of AC? The value of diagonal AC AC, it is very easy to see from the drawing that AC equals to AR plus RC. AR plus RC equals to AC. Okay, AR plus RC equals to AC. So AC equals to AR. We have already found out that AR equals to 12 minus A plus RC. We have already found out that RC equals also to 12 minus A. So actually we found out that AC equals to 12 minus A plus 12 minus A. So AC equals to 12 plus 12, that is 24. Minus A is minus 2A. So in conclusion, we found out that AC equals to 24 minus 2A. The diagonal AC of square ABCD equals to 24 minus 2A. We will focus on the right triangle, triangle ABC. In the right triangle, triangle ABC, according to Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here, the letters PT is abbreviation for Pythagoras theorem. The square of the hypotenuse is AC in this right triangle. The hypotenuse is AC, therefore the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to BC squared plus AB square. So I repeat again, in the right triangle ABC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, AC square equals to BC square plus AB square. We have already found out that AC equals to 24 minus 2A, therefore AC square will be equal to 24 minus 2A square, and it equals to BC square. BC is equal to 12 units. It is one side of square ABCD. So BC square will be equal to 12 square plus AB square. AB equals to 12 units. It is given as the equation, so AB square is 12 square. All the sides of the square are equal to each other. So if 12 square plus 12 square is 2 times 12 square, so according to equation number 1, 24 minus 2A square equals to 2 times 12 square. Here we'll take a root out of this equation, equation number 1, and we get that according to equation number 1, 24 minus 2A equals to the square root of 2, and the square root of 12 square will be equal to 12 because of the fact that the root cancels the square and we left only with 12. So in conclusion, we found out that according to equation number 1, 24 minus 2A equals to 12 times square root of 2. Here we will add to this equation, equation number 1, 2A, and we will subtract square root of 2 times 12, and we will get that according to equation number 1, A equals to 24 minus square root of 2 times 12. Here we will divide equation number 1 by 2. 2A over 2 is A, so A equals to 24 over 2 is 12, minus square root of 2 times, it is actually square root of 2 times 12. Twelve over 2 is 6. So it is minus 6 times square root of 2. In conclusion, we found out that according to equation number 1, A, that is actually also the radius of the circle, the radius of this circle, is equal to 12 minus 6 times square root of 2 units. Okay, in the next step, we will define the radius of the semicircle as B, that is to say, dn equals to B. The radius dn equals to B units. And the radius of the semicircle is also nt. So nt is also equals to B. What is the value of line segment TC? It is very easy to see from the drawing that TC will be equal to DC, that is actually 12 units, minus dn, that is actually B, minus nt, that is also B. So in conclusion, we found out that TC equals to 12 minus B, that is to say TC equals to 12 minus 2B. we can write down that TC equals to 12 minus 2B. In the next step, we will also find out the value of NC. It is very easy to see from the drawing. NC equals to NT plus TC. NT plus TC. So NC equals to NT, that is B, the radius of the semicircle, plus TC, that is 12 minus 2B. In conclusion, we found out that NC equals to 12 plus B minus 2B. That is to say, it equals to 12. B minus 2B is minus B. In conclusion, we found out that NC equals to 12 minus B. Here we also can write down that NC equals to 12 minus B. In the next step, we will join points N and S together by a straight line. Line segment NS start from the center of the semicircle, that is to say from point N, and ends at point S, that is a point on the semicircle itself. Therefore, NS is defined as the radius of the semicircle, that is to say, it equals to B units. And here, the radius NS, that is actually B, it is drawn to the point of tendency, that is to say, it is drawn to the point of tendency, that is point S, that is the point of tendency of tangent AC with this semicircle, and because of the fact that the radius NS is drawn to the point of tendency, then according to rule number 2, the tangent AC will be perpendicular to this radius NS. Again, the tangent AC will be perpendicular to this radius NS. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 2. Okay? And because of the fact that angle NSC is a right angle, it means that triangle NSC is a right triangle. So we will focus on the right triangle, triangle NSC, and we will derive we will implement the Pythagoras theorem on the right triangle, triangle NSC. The right great triangle, triangle NSC. So, here the hypotenuse of the right green triangle, triangle NSC is NC. I will repeat again, we will focus on the right green triangle, triangle NSC. By PT, that is Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right green triangle, triangle NSC is NC. Therefore, the square of the hypotenuse is NC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to NS squared plus SC squared. I repeat again. In the right green triangle NSC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, NC square equals to NS square plus SC square. We have already found out that NC equals to 12 minus B. Therefore, NC square will be equal to 12 minus B square. And it equals to NS square. NS is the radius of the semicircle, that is to say it equals to B, so NS square is B square plus SC square. We have already found out that SC equals to 12 minus 2A. And 12 minus SC here. You can see that SC equals to 12 minus 2A. Here, SC equals to 12 minus 2A. So SC squared is 12 minus 2A squared. But we have already found out that A equals to 12 minus 6 times square root of 2, so we'll find out the value of 12 minus 2A because we want to have only one variable that is missing, that is B. Okay, so we want to eliminate the variable A, so 12 minus 2A is equals to 12 minus 2 times A, and A equals to 12 minus 6 times square root of 2. That is to say, 12 minus 2A is actually equals to 12 minus 2 times 12 is minus 24, minus 2 times minus 6 times square root of 2 is plus 12 times square root of 2. So we have here 12 times square root of 2. 12 minus 24 is minus 12. In conclusion, we found out that 12 minus 2A is equal to 12 times square root of 2 minus 12. Okay, so here we will substitute 12 minus 2A in equation number 2 by 12 times square root of 2 minus 12. We'll do it now, and we'll get that according to equation number 2, twelve minus B squared is 12 squared plus b squared minus 2 times 12 times b, that equals to b squared, and we'll substitute 12 minus 2a squared by 12 times square root of 2 minus 12 squared So actually found out that according to equation number 2, 12 squared plus b squared minus 2 times 12 is 24, so it is minus 24b equals to b squared plus, here we will take 2 as a common factor out of this expression, and what left inside the brackets after we took 12 as a common factor from this expression, what is left is actually square root of 2. What is left from minus 12 after we took from it 12 as a common factor, what is left is actually minus 1 all square. So it is actually, we have b squared on both sides of the equation, so b squared will get cancelled, and we have here 12 squared minus 24b equals to, here we have 12 squared times square root of 2 minus 1 squared. So according to equation number 2, 12 squared minus 24b equals to 12 squared. So what is the value of square root of 2 minus 1 squared? Square root of 2 minus 1 squared is square root of 2 squared, that is 2, plus 1 squared, that is 1, minus 2 times square root of 2 times 1. So according to equation number 2, we found out that 12 squared minus 24b equals to, we will open the brackets on this side of equation number 2, and we'll get that it equals 12 squared times 2 is 2 times 12 squared plus 1 times 12 squared minus 2 times square root of 2 times 12 squared. So here we have 12 squared on both sides of equation number 2, so 12 squared will get cancelled, and we left with minus 24b is equals to 12 squared is 144, 144 times 2 is 288, minus 12 squared is 144, 144 times minus 2 is minus 188 times square root of 2. We will divide this equation number 2 by 24, and we get that according to equation number 2, minus b equals to 288 over 24 is 12, so it is 12 minus 12 times square root of 2. We will multiply equation number 2 by minus 1, and we will get that according to equation number 2, b equals to minus 12 plus 12 times square root of 2, or according to equation number 2, we actually found out that b equals to 12 times square root of 2 minus 12. Okay, so we actually found out the value of b, that is the radius of the semicircle. We found out the radius of the circle A, and in the next step we will join points A and R together by a straight line. We'll join points M and R together by a straight line, those 2 points. Line segment MR starts from the center of the circle, that is to say from point M, and ends at point R, that is a point on the circle itself. Therefore MR is the radius of this circle, that is to say it equals to A units. And here we have the radius MR. It is drawn to the point of tendency, that is to say it is drawn to point R, that is the point of tendency of tangent AC with this circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent, here the tangent AC, will be perpendicular to the radius Rn. AC is perpendicular to the radius Rn, according to rule number 2. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. This is according to rule number 2. And here, from point M, we will draw perpendicular on Rm. I repeat again, on Rm, we will draw perpendicular from point M. So here, this angle will be equal to 90 degrees, according to our construction. And in the next step, we will extend the radius NS until it intersects with the perpendicular from point M. Okay? And we will define the intersection point of the extended NS and the perpendicular from point M as X. Okay? Here we will focus, first of all, NS is the radius of the semicircle. It equals to B. This is the radius of the semicircle. NS is the radius. It is absolutely a straight line. NS is a straight line, and when we extended the straight line NS by a straight line, then we got NX, that it is still must be a straight line. Okay? When you extend a straight line by a straight line, it also still must a straight line. So NX is a straight line. I'll write it down. NX is a straight line. Okay? Here, NX is a straight line. And we actually have also rule number 4. According to rule number 4, the sum of the angles on one side of a straight line is equal to 180 degrees. I repeat rule number 4 again. According to rule number 4, the sum of the angles on one side of a straight line is equal to 180 degrees. And we know that nx is a straight line, because when you extend a straight line, by straight line it is a straight line, so nx is a straight line. And if we focus on this side of the straight line nx at point S, then the sum of the angles must be equal to 180 degrees. So which angles we have at point S on this side of the straight line nx? We have here 90 degrees, and we also have angle RSX. So the sum of those two angles must be equal to 180 degrees according to rule number 4. I repeat again, the sum of the angles on one side of the straight line nx at point S must be equal to 180 degrees. That is to say 90 degrees plus the size of angle RSX. In total they must be equal to 180 degrees according to rule number 4. We will subtract 90 degrees from this equation and we will get that angle RSX is equal to 180 degrees minus 90 degrees equals to 90 degrees. So we found out that this angle RSX, is a right angle, it equals to 90 degrees. In the next step we will focus on quadrilateral RMSX. The quadrilateral RMSX, this quadrilateral we have 1, 2, 3 right angles, and the sum of 3 right angles is 90 times 3, 270 degrees, plus the size of the fourth angle, that is actually angle MXS, so in total the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We will subtract 270 degrees from this equation and we will get that the size of angle MXS is equal to 360 degrees minus 270 degrees. It is equal to 90 degrees. Actually it is a right angle. So we found out that the missing angle here in quadrilateral RMSX is a right angle, that is to say it equals to 90 degrees. So actually, because of the fact that in quadrilateral RMSX we have 4 right angles, Therefore, quadrilateral RMSX is at least a rectangle. Quadrilateral RMSX is at least a rectangle. And we know that the opposite sides of a rectangle are equal to each other according to rule number 3. That is to say, Rm equals to Sx. In rectangle RMSX, Rm must be equal to Sx. Rm equals to Sx according to rule number 3. But we have already found out that Rm equals to A. It is the radius of this circle. It equals to A. So from this equation, A equals to Rm equals to Sx, we will conclude that Sx is also equals to A. You can write here that Sx equals to A. Likewise, in rectangle RMSX, Rs must be equal to Mx. According to rule number 3, that the opposite sides of a rectangle are equal to each other. But we have already found out that Rs equals to A. Here, Rs equals to A. So we can write here that Rs equals to A. From this equation, A equals to Rs equals to Mx, we will conclude that Mx is also equals to A. Okay, here Mx equals to A. And triangle NMX is a right triangle because of the fact that angle MXN is a right angle. So we'll focus on the orange triangle. Triangle M and X, and we will implement the Pythagoras theorem on the orange triangle, triangle M and X. Okay. So, in the orange triangle, triangle M and X, the orange right triangle, triangle M and X, according to the Pythagoras theorem, PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the orange triangle is Mn, therefore the square of the hypotenuse is Mn squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to Mx squared plus Nx squared. I'll repeat again. In the right triangle, right orange triangle, triangle M and X, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is Mn, so Mn squared must be equal to Mx squared plus Nx squared. mn is the missing variable, so we leave it as it is. Mn squared equals to mx squared. We already found out that mx equals to a, so mx squared will be equal to a squared plus nx squared. Nx equals to b plus a, or a plus b. Therefore, nx squared will be equal to a plus b squared. A plus b squared. We have already found out the values of a and b, so I write it down. I write it down. We have already found out that a equals to 12 minus 6 times square root of 2. B equals to minus 12 plus 12 times square root of 2. And what is the value of a plus b? A plus b equals to 12 plus minus 12 is 12 minus 12, that is 0. And here we have 12 times square root of 2 minus 6 times square root of 2 is 6 times square root of 2. So we found out that a plus b equals to 6 times square root of 2 units. We will put these values inside the equation number 3 in order to find out the value of the variable that we are looking for, that is actually mn. Okay. So according to equation number 3, mn squared equals to a squared. A is 12 minus 6 times square root of 2, and we have to square it. It is a squared plus a plus b squared. We just right now found out that a plus b equals to 6 times square root of 2, so a plus b squared will be equal to 6 times square root of 2 squared. Here we will open the brackets on this side of equation number 3, and we will get that according to equation number 3, mn squared equals to 12 minus 6 times square root of 2 squared is 12 squared plus 6 times square root of 2 squared is 6 squared is 36, and square root of 2 squared is 2, 36 times 2 is 72. Minus 2 times 12 times 6 times square root of 2 plus, again, 6 times square root of 2 squared is 6 squared, that is 36, times 2, that is 72. So, in conclusion, we found out that mn squared, according to equation number 3, equals to 12 squared, that is 144, plus 72 plus 72 is 144, and 144 plus 144 is 2 times 144, so here it is 2 times 144, minus, this is minus here, 6 6 times 2 is 12, and 12 times 12 is 144. So here, this expression in total, in conclusion, equals to 144 times square root of 2. Here we take a common factor of 144 out of these expressions, and we will get that, according to equation number 3, 144 is a common factor of those two expressions. So inside the brackets, what is left from this expression after we took from it 144? What is left? It is actually 2. What is left from this expression after we took from it 144 is a common factor. What is left? It is actually square root of 2. And it is equal to mn squared. Here we'll take a root out of this equation number 3, and we will get that the value of mn is equal to the square root of 144 is 12 times the square root of 2 minus square root of 2. Okay? Or in terms of numbers, it equals to 9.18 units. So the answer to the question is that the distance between the centers of the semicircle and the circle, that is to say mn, is equals to either 12 times square root of 2 minus square root of 2, all in square, or it is equal to 9.18 units. Okay? That is the answer to the question. In the next step, I will summarize the lecture. Actually, we wanted to find out the distance between the centers of the semicircle and the circle. The center of the semicircle is at this point N, and the center of this circle is at point M. And we want to find out the distance between the centers, that is to say, we want to find out the length of line segment MN. Okay? And we have here square ABCD. One side of square ABCD equals to 12 units, and we have inside the square this circle. Actually, this circle is tangent to the square at 2 points. Point P is the point of tendency, point Q is the point of tendency of the circle with the square. And in the third point, that is here, point R, this circle is tangent to diagonal AC. R is the point of tendency. And the semicircle is tangent to the square at point D, and it touches the square also at point T. Okay? So first of all, we defined PB as A. So if PB equals to A, then AP will be equal to AB minus PB. That is to say, AP will be equal to AB, that is 12, minus PB, that is A. In conclusion, AP equals to 12 minus A. Then I presented to you rule number 1. According to rule number 1, a tangent to a circle, the length of two tangents from a common external point to a circle are equal. So if we have this circle and we have the point P that is external point, why point P is external point in relation to this circle? Because point P is not located inside this circle, nor on this circle, but it is located outside this circle. Therefore point P is defined as an external point in relation to this circle. So if from the external point P we will draw two tangents to this circle, the first tangent is tangent PA, is the point of tendency of the first tangent with the circle, and we also draw, we draw the second tangent, that is tangent PB. B is the point of tendency of this tangent with this circle. So the length of the first tangent is PA, the length of the second tangent is PB, and according to rule number 1, the lengths of those two tangents are equal to each other. That is to say, PA is equal to PB. So whenever you draw two tangents from an external point of a circle to that circle, then the lengths of those two tangents will be equal to each other. Okay, in this case, PA equals to PB. And we actually implemented rule number 1 in our drawing. Here we have point B. Point B is defined as an external point in relation to this circle. From point B we have two tangents to this circle. The first tangent is BP, the second tangent is BQ. And according to rule number 1, they are equal to each other. That is to say, BP equals to BQ. Okay, so here, according to rule number 1, BP equals to BQ. But according to our definition, BP equals to A. So we can write here that BP equals to A. From this equation, A equals to BP equals to BQ, we conclude that BQ is also equals to A. Here BQ equals to A. Then we have at point A, we have tangent AP to this circle and tangent AR to this circle. And according to rule number 1, the lengths of those two tangents will be equal to each other. That is to say, AP equals to AR. According to rule number 1, AP equals to AR. But we have already found out that AP equals to 12 minus A. So from this equation, 12 minus A equals to AP equals to AR, we will conclude, we will derive that AR is also equals to 12 minus A. So we can write here that AR is also equals to 12 minus A. Okay, then we focus at point C. From point C, we have, in relation to this circle, from the external point C, we have tangent CQ and we have tangent CR to this circle. And whenever you have two tangents from an external point to a circle, then the lengths of those two tangents will be equal to each other. That is to say, CQ equals to CR. According to rule number 1, CQ equals to CR. But here, we have already found out that CQ is equals to 12 minus A. So from this equation, 12 minus A equals to CQ equals to CR, we will conclude that CR is also equals to 12 minus A. So we can write here that CR equals to 12 minus A. Then we return to point A. From point A, from the external point A, we have two tangents to the semicircle. The first tangent to the semicircle is tangent AD. Tangent AD is tangent to this semicircle at point D. Point D is the point of tendency. And we have also the second tangent that is actually tangent AS. And according to rule number 1, those two tangents must be equal to each other. That is to say, AD equals to AS. Again, according to rule number 1, in relation to the external point, point A, and the semicircle that we have here, the two tangents to the semicircle that existed from the external point, point A, must be equal to each other. That is to say, AD must be equal to AS. But it has given us the question that AD is the one side of the square, it equals to 12 units. So from this equation, we will derive that AS is also equals to 12 units. So we can write here that AS, this line segment, equals to 12 units. And what is the value of RS? It is very easy to see from the drawing that RS equals to AS minus AR. Again, RS equals to AS minus AR. We just right now found out that AS equals to 12 units, AR equals to 12 minus A. Therefore, RS will be equal to 12 minus 12 minus A. We open the brackets here, and we got that RS equals to 12 minus 12, that is 0, plus A. So in conclusion, we found out that RS equals to A units. This line segment RS equals to A units. Okay? Then I present to you rule number 2. According to rule number 2, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle, then the center of this circle is this point, point O. And we have tangent AB is tangent to this circle at this point. This is the point of tendency. We defined point M, that is the point of tendency. The point that the tangent AB touches this circle is at point M. So point M is the point of tendency. So here we have the radius OM, it is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. Therefore, whenever we have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to MO, the radius. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to the radius. In this case, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Then we implemented rule number 3 in our drawing. First of all, we joined points P and M together by a straight line. PM is the radius of this circle because it starts from the center of the circle, that is to say from point M, and ends at point P, that is the point on this circle itself. Therefore, PM is the radius of this circle. And here we have the radius MP, it is drawn to the point of tendency, that is to say it is drawn to point P, that is the point of tendency of tangent AB with this circle. Therefore, in this case, the tangent AB will be perpendicular to the radius PM. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay? And we also know that all the angles inside the square are right angles. So angle ABC must be equal to 90 degrees in square ABCD. And we join points M and Q together by a straight line. MQ is the radius of this circle because of the fact that it starts from point M and ends at point, that is the center of the circle, and ends at point Q, that is a point on this circle itself. And this is exactly the definition of the radius. So MQ is the radius of this circle, and we have the radius MQ that is drawn to the point of tendency. That is to say, it is drawn to point Q, that is the point of tendency of tangent BC with this circle. Therefore, according to rule number 1, the tangent BC will be perpendicular to the radius MQ. The tangent BC will be perpendicular to the radius QM, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay, then we focused on the quadrilateral PBMQ. In quadrilateral PBMQ we have 3 right angles, 1, 2, 3, and the sum of 3 right angles is 270 degrees. So here, in quadrilateral PBMQ, the sum of 3 right angles is 270 degrees, plus the size of the fourth angle that is actually angle PMQ. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation and found out that angle PMQ equals to 90 degrees. So this angle equals to 90 degrees, therefore quadrilateral PBMQ that has 4 right angles must be at least a rectangle. Okay, so we relate to quadrilateral PBMQ as a rectangle, and we have rule number 3 that states that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle PBMQ, PB must be equal to MQ. According to rule number 3, PB must be equal to MQ, but PB equals to A according to our definition. So from this equation, A equals to PB equals to MQ, we will conclude that MQ is also equals to A. Here, MQ is also equals to A. Likewise, in rectangle PBMQ, PM must be equal to BQ according to rule number 3. PM equals to BQ, but we already found out that BQ equals to A. You can write here that BQ equals to A, and from this equation A equals to BQ equals to PM, we will conclude that PM is also equals to A. Here PM is equals to A, so we actually found out that quadrilateral PBMQ is a square. It's not a rectangle, but it is a square. Again, quadrilateral PBMQ is a square because of the fact that all of its sides are equal to each other, they are equal to A. That is the radius of this circle. And what is the value of SC? The value of line segment SC is very easy to see from the drawing that it equals to RC minus RS. Again, RC minus RS equals to SC. Again, SC, according to the drawing, it is very easy to see that SC equals to RC minus RS. But we've already found out that RC equals to 12 minus A. And RS, we already found out that RS equals to A, so in conclusion, SC equals to 12 minus A, that is to say, SC equals to 12 minus 2A, 12 minus 2A. Okay, and what is the value of diagonal AC? Diagonal AC, from the drawing, it is very easy to see that diagonal AC equals to AR plus RC. Again, diagonal AC equals to AR plus RC. We already found out that AR equals to 12 minus A, and RC is also equals to 12 minus A. So in conclusion, we found out that AC equals to 12 plus 12, that is 24. Minus A is minus 2A. So in conclusion, we found out that the length of diagonal AC of square ABCD is 24 minus 2A. Okay, then we focused on the right triangle ABC, and we implemented the Pythagoras theorem on the right triangle ABC. In triangle ABC, by PT, Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, so the square of the hypotenuse is AC square. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to BC square plus AB square. We have already found out that AC equals to 24 minus 2A. So if AC equals to 24 minus 2A, then AC square will be equal to 24 minus 2A square. That equals to BC square. BC equals to 12, so BC square equals to 12 square, plus AB square. AB equals to 12, so AB square is 12 square. And there, 12 square plus 12 square is 2 times 12 square. So here we took a root out of this equation, equation number 1, and we found out that 24 minus 2a equals to the square root of 2 times the square root of 12 square, and the square root of 12 square is 12 because of the fact that the root cancels the square and we left only with 12. So in conclusion, we found out that 24 minus 2a equals to square root of 2 times 12. Here we added to this equation 2a and we subtracted square root of 2 times 12. And we found out that 2a equals to 24 minus square root of 2 times 12. We divided this equation number 1 by 2, and we got that a equals to 24 over 2 is 12, and 12 over 2 is 6. So in conclusion, we found out that a, that is the radius of the circle, equals to 12 minus 6 times square root of 2 units. Okay, then we defined the radius of the semicircle as b, that is to say dn, that is the radius of the semicircle, is b, and nt, that is also the radius of the semicircle, is defined as b. And here, what is the value of tc? Tc equals to dc minus dn minus nt. Tc equals, that is to say, it equals to dc, that is 12, minus dn, that is b, and tn, that is also b, that is to say tc equals to 12 minus b, that is to say tc equals to 12 minus 2b. Here tc equals to 12 minus 2b. And then what is the value? We join together points n and s together. We join points n and s together by a straight line. ns is the radius of the semicircle because of the fact that it starts from the center of the semicircle, that is to say from point n, and ends at point s, that is a point on this semicircle itself. Therefore, ns is the radius of the semicircle, that is to say it equals to b. We have the radius ns that is drawn to the point of tendency, that is to say ns is drawn to the point of tendency, that is point s. Therefore, whenever we have a radius that is drawn to the point of tendency, then the tangent AC will be perpendicular to the radius ns. The tangent AC will be perpendicular to the radius ns according to rule number 2. That is to say, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. And because of the fact that angle NSC is equal to 90 degrees, then the green triangle NSC, is a right angle. So we can implement the Pythagoras theorem on the green right triangle NSC. And what is the value of the hypotenuse NC of the right green triangle NSC? The hypotenuse equals to NC plus TC. The hypotenuse NC equals to NT plus TC. Again here, the hypotenuse NC of the green right triangle equals to NT plus TC. NT is the radius of the semicircle, that is to say it equals to b, and TC equals to 12 minus 2b. So NC equals to 12, and b minus 2b minus b. So in conclusion, I found out that the hypotenuse NC of the green right triangle equals to 12 minus b. So here, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, nc square equals to ns square plus sc square. In the right triangle NSC, by Pythagoras theorem, the square of the hypotenuse, that is to say nc square, equals to ns square plus sc square. We have already found out that nc equals to 12 minus b, so nc square will be equal to 12 minus b square. That equals to ns square. Ns equals to b, so ns square is b square. Sc equals to 12 minus 2a, so sc square will be equal to 12 minus 2a square. We open the brackets here. Actually, here we have 12. Here we have 12 minus 2a, so we want to get rid from a because we we should have only one variable that is missing. In order to find out the value of b, we must eliminate a. And we already know that the value of a is 12 minus 6 times square root of 2. So what is the value of this expression 12 minus 2a? 12 minus 2a will be equal to 12 minus 2 times a, and a equals to 12 minus 6 times square root of 2. So here we have 12 minus 2a equals to 12 minus, we open the brackets here, 2 times 12 is 24, and 2 times minus 6 times square root of 2 is minus 12 times square root of 2. Here we have 12 times square root of 2, and 12 minus 24 is minus 12. So in conclusion, we found out that 12 minus 2a equals to 12 times square root of 2 minus 12. Okay? 12 minus 2a equals to 12 minus 2a equals to 12 times square root of 2 minus 12. So we can substitute 12 minus 2a in this equation, equation number, we can substitute 12 minus 2a in this equation, equation number 2, by 12 times square root of 2 times minus 12. This expression, we did it, and we got that according to equation number 2, here, actually, we have here 12 minus b square is 12 square plus b square minus 2 times 12 times b, that equals to b square plus 12 minus 2a, but 12 minus 2a equals to 12 times square root of 2 minus 12, according to what we just right now found out. So we substituted 12 minus 2a by 12 times square root of 2 minus 12 square, and we got here 12 square plus b square minus 2 times 12 is minus 24, so here we will have in conclusion minus 24b, that equals to b square plus, here we took 12 as a common factor out of this expression, so inside the brackets what we have from this expression, we left only with square root of 2, and from minus 12 we left only with minus 1, after we took 12 as a common factor from it. So here the expression is 12 times square root of 2 minus 1, all inside the square. So here we have b square in this side of the equation and b square on the other side of the equation, so b square will get cancelled, and we left only with 12 square minus 24b equals to, here 12, here we have square on 12, so it is 12 square times square root of 2 minus 1 square. So we have here 12 square minus 24b, that equals to 12 square. We open, and we calculated the value of square root of 2 minus 1 square. Square root of 2 minus 1 square equals to 2 plus 1 minus 2 times square root of 2. Okay, so here we have 12 square on this side. No, here we open the brackets, and we got 12 square minus 24 equals to 12 square times 2 is 2 times 12 square. 12 square times 1 is 12 square. And we have minus 2 times 2 times 12 square. We have 12 square on both sides of the equation, so 12 square will get cancelled. And we left only with minus 24b, that equals to, here we have, actually, 12 square is 144, and 144 times 2 is 288, and here also we have minus 12 square, that is minus 44 times 2 is minus 288 times square root of 2. Here we divided this equation by 24, and we got that minus b equals to 288 over 24 is 12. And minus 288 square root of 2 over 24 is minus 12 times square root of 2. We multiplied this equation number 2 by minus 1, and we got that b equals to 12 times square root of 2 minus 12. So we found out the value of a, we found out the value of b, and in the next step we join points M and R together by a straight line. MR is the radius of this circle, that is to say it equals to A, and the radius MR, it is drawn to the point of tendency, that is to say it is drawn to point R, that is the point of tendency of tangent AC with this circle. Therefore, according to rule number 2, the tangent AC will be perpendicular to the radius MR. That is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Then from point M we draw perpendicular on RM. That is to say this angle equals to 90 degrees. And then we extended the radius NS in such a way until it intersects with the perpendicular from point M, and we define the intersection point between the extended NS and the perpendicular from point M as X. So here we have quadrilateral RM XS, and we know that NS is the radius of the semicircle, that is to say it is absolutely a straight line. And when you extend a straight line, then the result will be still a straight line. The result that we will get will be still a straight line. So when we extended the straight line NS until point X, we still got a straight line. NX must be still a straight line, because when you extend the straight line, then by a straight line it must be still a straight line. So NX is a straight line. So we can write down that NX is a straight line, and we have rule number 4 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So here, if we focus, we know that NX is a straight line. If we focus on this side of the straight line NX, on this side of the straight line NX, at point S, then the sum of the angles must be equal to 180 degrees according to rule number 4. Which angles we have on this side of the straight line NX at point S? We have here 90 degrees, and we have also angle RSX. So in total the sum of those two angles must be equal to 180 degrees according to rule number 4. 90 degrees plus the size of angle RSX must be equal to 180 degrees according to rule number 4. We subtracted 90 degrees from this equation and found out that angle RSX equals to 90 degrees, because 180 degrees minus 90 degrees is 90 degrees. So we found out that this angle is a right angle. So actually in quadrilateral RMSX we have 1, 2, 3 right angles. And the sum of 3 right angles is 270 degrees, plus the size of the fourth angle, that is actually angle MXS. In total, they must be equal to 360 degrees. Again, the sum of 3 right angles, that is 270 degrees, plus the size of the fourth angle must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation, and we got that the size of angle MXS is 90 degrees. So this angle is a right angle. So actually we found out that all the angles inside quadrilateral RMXS are right angles. It has 4 right angles, and therefore quadrilateral RMSX is at least a rectangle, if not a square. And we know that the opposite sides of a rectangle are equal to each other. That is to say, RM must be equal to SX in rectangle RMSX. RM equals to SX according to rule number 3. But we have already found out that RM is the radius of this circle, that is to say it equals to A units. RM equals to A. So from this equation, A equals to RM equals to SX, we will conclude that SX is equals to A. Here SX equals to A. Likewise, in rectangle SRMX, according to rule number 3, RS equals to MX. Okay, according to rule number 3, RS equals to MX. But we have already found out that RS equals to A. So we can write here that RS equals to A. From this equation, A equals to RS equals to MX, we will conclude that MX is also equals to A. Here, MX is also equals to A. Then we focus on the orange right triangle, triangle MXN, and we implemented the Pythagoras theorem on the right orange triangle, triangle MXN. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is mn, so the square of the hypotenuse is mn squared. It must be equal to mx squared plus xn squared. In the right triangle MXN, according to the Pythagoras theorem, mn squared must be equal to mx squared plus nx squared. So mn squared must be equal to mx equals to a, so mx squared is a squared plus nx squared. Nx squared equals to nx equals to b plus a, or a plus b, it is the same. So nx squared equals to a plus b squared. Okay. We have already found out that a equals to 12 minus 6 times square root of 2, b equals to minus 12 plus 12 times square root of 2. What is the value of a plus b? It is very easy to see that a plus b equals to minus 12. 12 plus minus 12 is 12 minus 12, that is 0. And we have here 12 times square root of 2 minus 6 times square root of 2, that is actually 6 times square root of 2. So in conclusion, we found out that a plus b equals to 6 times square root of 2. So here we have mn squared equals to, we substituted a by 12 minus square root of 2. So it is a squared, it is 12 minus square root of 2 squared, plus a plus b squared. We just right now found out that a plus b equals to square to 6 times square root of 2. So a plus b squared will be equal to 6 times square root of 2 squared. So we have, according to equation number 3, mn squared equals to, here we open the brackets, 12 minus 6 times square root of 2 squared is 12 squared, plus 6 times square root of 2 squared is 6 squared is 36, times square root of 2 squared is 2, and 36 times 2 is 72, minus 2 times 12 times 6 times square root of 2, plus 6 times square root of 2 squared is 6 squared is 36, square root of 2 squared is 2, and 36 times 2 is 72. So we have here 12 squared is 144. 72 plus 72 is 144. So we have 2 times 144, minus 2 times 6 is 12, and 12 times 12 is 144. So in conclusion, this expression equals to minus 144 times square root of 2. So in conclusion, we got that according to equation number 3, mn squared equals to 2 times 144 minus 144 times square root of 2. We took 144 as a common factor out of those two expressions. So what is left from this expression after we took from it 144? What is left from this expression is 2. What is left from this expression after we took from it 144 is a common factor. What is left from it is actually minus square root of 2, and it equals to mn squared. We took a root out of this equation, equation number 3, and we got that mn equals to square root of 124. The square root of 144 is 12, and times the square root of 2 minus square root of 2. So in conclusion, we found out that mn, the distance between the center of the semicircle and the center of the circle, mn equals to either 12 times square root of 2 minus square root of 2 units. So in terms of numbers, it equals to 9.18 units. Again, the value of mn equals to either 12 times square root of 2, 2 minus square root of 2 units, or in terms of numbers, mn equals to 9.18 units. Okay, thank you very much.